All right, we're back for the very last three guys. I promise we have three more people, and then we will stop harassing you with history. So Ernest Rutherford's probably the biggest guy that we have left. He's from New Zealand, so he probably had a very cool accent, which is very interesting. And then basically what happened was he did two things. The first thing he did was discover radiation. And radiation, if you think about, has to do with like nuclear energy, and you can think of like nuclear bombs, stuff like that. But he actually discovered the two types. And we actually know that there's more than that now, but he discovered alpha and beta radiation. So that was the first thing he did. And then the second thing he did is he used this radiation, he used these alpha particles in what's called the gold foil experiment. And basically what he did was he actually, and we'll have a picture of it in a second, well actually we can go to it and then we'll come back. What he did was he had this gold foil, and if you remember, gold foil is very, very malleable. Gold's the most malleable thing in the world. So what happened was he had this gold foil that was very, very thin, like a couple atoms thick. And what he did was he would take this alpha particle emitter and actually shoot particles at it. And if you remember, if we go back, we are still operating under the idea of this plum pudding model, these pluses and minuses. So what they thought was going to happen was he was basically trying to prove J.J. Thomson right, this gold foil experiment. So what he thought was going to happen is he was going to have these alpha particles. They were going to go through the actual the atom, and then when they got close to a positive or a negative, they would kind of bend a little. Not a lot, not a huge deal, but just a little. And if he saw that, it was going to be the plum pudding model. So what he saw down here, he thought the positive charges were oops, hold on, let me erase that so that you can actually read. Again, he just thought it was the plum pudding model. So he thought that these positive charges were evenly distributed, and what he saw was as these alpha particles are positive, so when it got near one of these positive things, it would deflect a little tiny bit. So that's what he was expecting. And then what he actually found was the vast majority went straight through. So if you look in here, it's just at the very thing. If you look at your notes results, most of the alpha particles passed right through the foil. It didn't bend at all. Some, very few, would kind of deflect, so you can see there was a couple that did have some angles to it. And then basically 1 out of every 8,000 would actually kind of bounce back and almost come back and hit him. And basically what it did was it kind of caused an uproar because it disproved the atomic theory of J.J. Thomson. They kept repeating the experiment. They couldn't believe it. But every time they did it, what happened was the same thing. So what they came up with was that they had to change the atomic model for the kind of final time. And they still knew there were positives and negatives, but they said, okay, they can't just all be spread throughout the atom. And what they came up with was our nucleus. So what they came up with was they have this very dense center where all the positive is, and that's our nucleus. The nucleus is where all the positive charges, and it's where 99.9% of the mass is. So that's basically all of it. And then we have these electrons that are going to float around the nucleus. And they're going to be moving at a high speed. And then this is the big one. Atoms do not have a uniform density because most of their mass is in the middle, and then the electrons are going around it. So the volume of the nucleus is really, really small compared to the total volume of the atom. So to give you an idea, if we went out to the soccer field and I had thrown a dime out in the middle of the soccer field somewhere, and I told you guys to go find it, and somewhere in the soccer field, the dime would be the nucleus. The total volume of the entire atom would be like the whole soccer field. So the nucleus is really small but very, very heavy. And you can see down here, the atom is 10,000 to 100,000 times bigger than the nucleus itself. And again, if you look back, just one more time here, if you look, these alpha particles were coming in, and most of the time they didn't even touch the nucleus. So most of the time they went straight through. Sometimes, like up at the very top, they'd be coming in, and then they'd get close to a nucleus, and then they'd kind of bend away from the nucleus a little bit, again with my bad drawing. And then very, very, very few times when the alpha particle would come in, it would actually hit the nucleus and kind of bounce back. And that's kind of what proved that J.J. Thomson's model was not correct. All right, so we have 2 more guys, and then you are all done and free. So here we go. I forgot one thing, sorry. Ernest Rutherford, what he did come up with a new model, and he came up with the last one, and he actually came up with the nuclear model. He did say that there had to be something else in the nucleus, because for 2 reasons. 1, there wasn't enough mass, and 2, what he said was if all those positive protons were sitting in the middle, why aren't they repelling each other? So he did say that there had to be another part of the atom. He didn't really know what it was. But he came up with this nuclear model with this nucleus in the middle and the electrons outside of it. So that was his big thing. And now for real, I promise, the last 2 guys. Henry Moseley, he came up with this thing, and really all you need to know, all you need to underline is that he came up with this thing that every element has its own special atomic number. He used cathode ray tubes, he used all this kind of stuff, but basically he saw that every element has its own unique nuclear charge. That's what kind of makes the element the element. And the very last guy that you'll ever have to hear about in chemistry is good old James Chadwick, and he kind of came up and he was the one that said, he actually went along with what Ernest Rutherford said, and he was able to isolate a neutron. And neutrons are kind of the hardest to get because they aren't charged, so they kind of just sit there and they don't actually, you can't use a magnet to get them. They were harder to get. So they got the mass, and it was actually the heaviest of all of them. And now obviously they're still really small, but the charge of a neutron is no charge, and it's the heaviest subatomic particle. And that's good old James Chadwick. All right, and then just so you don't have everything, here's a little comic relief. If you now know about electrons, protons, and neutrons.